Today what we're going to be learning about is atomic structure in the periodic table. Now before you get too far into this presentation, you are going to need to find your own periodic table as we will be looking at numbers on it. So the first thing that we're going to look at is we're actually going to look at the definition of what an atom is. And what an atom is the smallest particle of an element that retains the properties of that element. The smallest particle of an element that retains the properties of that element. The folks that first thought about that were the Greeks a long time ago. 4th century BC, a fellow named Democritus is actually the one who coined the term atom, which does mean a tiny indivisible part. Get a little bit more modern, we have Dalton's atomic theory, which describes the behavior of atoms, what an atom is, and how they interact with other atoms. And his theory consists of four parts. The first part is that all elements of a compound are made of tiny indivisible parts called atoms. Now make sure when you're writing this down that you actually are writing indivisible, not invisible. I mean, yes, we can't actually see atoms with the naked eye, but what he's talking about here is that they can't be broken down into anything more simple. The second part of his theory says that atoms of the same element are the same, and atoms of different elements are different, and that seems quite obvious. The third part, he says that atoms of different elements can combine in simple whole number ratios to form compounds, meaning that we'll have compounds like H2O, but not compounds like H2O1/2. And lastly, he says that chemical reactions occur when elements are separated, joined, or rearranged. However, one element cannot be changed into another element, which was disproving some of the things that the alchemists had been trying to do over the centuries. Now, probably when you were listening to that, you were thinking, well, some of those things really aren't true anymore, at least with the technology that we have today. The first part about atoms being indivisible, well, in a way it's kind of true. If we want an atom to be the same atom, if we want an atom to be copper or gold, well, yeah, truly it is indivisible. However, with today's technology, we know that atoms are made up of subatomic particles and that we can divide them if we had to. However, the particles that remain, the protons, the neutrons, electrons, do not retain the properties of whatever that element was. A proton from copper should look identical to a proton, say, from a hydrogen. The second part about all atoms of the same element being the same seemed obvious. However, all copper atoms are not identical. All carbon atoms are not identical. There actually are slight differences between them, and those are known as isotopes, which we'll talk about a little bit later on in the notes. The third statement about how atoms join in simple whole number ratios actually is indeed true. But the last part, where it talks about that one element cannot be changed into another element, they actually can be changed into other elements. Now, can you or I do it? No, not in my lab and not with the facilities that I have. However, in special labs, supercolliders, they can actually form new elements. That's how they create new elements when we find new ones every once in a while. That's also how we can split atoms as well and create, again, additional atoms. So let's talk about the different subatomic particles. The first one that we're going to look at is the proton, which has a positive charge. And I also told you the mass. It's got a mass of about 1.67 times 10 to the negative 24th grams, which is really, really, really tiny. But we'll look at that and compare it to the other subatomic particles here in a second. Now, if I needed to know the number of protons for a particular atom, all I would simply do is look at the periodic table and find the atomic number. The atomic number on the periodic table is the whole number that is in each block. For instance, hydrogen has an atomic number of 1, so I know it has 1 proton. Helium has an atomic number of 2, so it has 2 protons, and so on. The next subatomic particle that we're going to look at is the electron. An electron has a negative charge. Now its mass is 9.11 times 10 to the negative 28th. So it is approximately 2,000 times smaller than a proton is, so electrons are even more tiny. Now, to determine the number of electrons in an atom, for right now and in this chapter, we're going to say that it's going to be equal to the number of protons because we're going to be dealing with neutral atoms. However, in the future, when we look at atoms, we're going to discover that not all atoms will be neutral. But for right now, that's how we're going to calculate it. And then the last subatomic particle we're going to look at is the neutron. Neutrons have no charge, so they have a neutral charge. Their mass is about 1.67 times 10 to the negative 24th. So they are the same size as a proton is. Now, to determine the number of neutrons in an atom, we have to do a little bit of math. So what we do is we look at the atomic number mass, and then we round that number, and then we subtract off the atomic number. And so as an example, if we looked at beryllium, beryllium has an atomic mass of 9.012, so we would round that to 9, and then we could subtract off the atomic number, which is 4, and we would be left with 5 neutrons. So an average atom of beryllium has 5 neutrons. We could do the same process with magnesium, which is underneath. Magnesium's mass is about 24.3, so again we round it to 24, subtract off 12, and magnesium has 12 neutrons. So let's talk about some other parts of the atom. The center of the atom is called the nucleus. That's where the protons and neutrons hang out. That's where most of the mass is at. And so because it's all concentrated there, the nucleus is extremely dense. Outside of the nucleus is where the electrons are found, and they are found on the outside edges of the atom in areas called electron clouds. The next thing we're going to look at is we're going to look at some clip art. I've been trying to scatter some different atom clip art throughout this presentation, not only to make it decorative, but so that we could kind of look and see about what kind of characteristics this clip art has. They all pretty much look the same. However, there are lots of things wrong with the clip art. The first thing is that I seriously doubt the electrons in the nucleus are colored, and if they were, why are those electrons different colors? I have no idea. Secondly, has to do with size. Even if that nucleus represented a single proton or a single neutron, it would have to be 2,000 times bigger than one of the electrons surrounding it. Currently, if we look at it, it might be 20 or 30 times bigger, but certainly not the 2,000 times bigger that it would need to be. And if it were indeed a nucleus that had multiple protons and neutrons, it would have to be humongous compared to those little electrons on the outside. Next has to do with the paths. The paths of electrons travel are actually wave-like. They're more buzzy and vibrational, not these smooth orbits that a diagram typically draws around it. And lastly, which is probably the most interesting, is the distance between the nucleus and the electrons. They are way too close in this picture. In order to have this drawn correctly, if that were a nucleus, and that's the size it was, about 1/2 inch in diameter, then those electrons, the nearest electrons, would have to be 360 feet away. Certainly wouldn't fit on a piece of paper, but that's how it would have to be in order to be correct. So here's a question for you. What's in all that space between the nucleus and electrons if they're really that far apart? Can't be air. That's made up of atoms. Well, the truth is it's nothing. Most of an atom's space is absolutely nothing. So the next thing I'd like to do is maybe do a little bit of practice. And so this is where you need your periodic table for sure. And so when we look at boron, the first column there is asking its atomic number. So when we look at boron, we can see its atomic number is 5, which means that the atomic number is equal to the number of protons, so it also has 5 protons. They gave you the information for neutrons. The electrons, well, they would have to be equal to the protons, so that's going to be 5. And then the atomic mass pretty much is just the protons and neutrons added together. So that should be right about 11. On the next line down, we have sodium. And sodium evidently has an atomic number of 11 because it tells us that. Well, the atomic number is 11, then the protons are also 11. The neutrons, we have to subtract for neutrons. So we need to know the atomic mass. They tell us the atomic mass is 24. So 24 minus 11 is 13. Next we have the electrons. Well, electrons are equal to protons for the stuff we're doing now, so that's going to be 11. Okay, well the next one, they don't tell us what element it is. So we have to kind of figure that out. So protons or neutrons? I'm going to go with protons. Protons are going to help us figure out what element that is. So let's find 31 on the periodic table. And we do that, we find that number 31 is gallium, so its symbol is Ga. So if gallium is number 31, that means the atomic number is 31. We were told that the neutrons are 37, so the electrons have to be equal to the protons, so that's 31. And then if we add those two together, the protons and neutrons, that should give us our atomic mass. So that's going to be 68. And then on the last one, well, we know it's a neutral atom, so the electrons and protons have to be the same, which means the number of protons is 39, which means the atomic number is 39. So let's look on the periodic table for 39. There it is. Well, that's a fun symbol. Okay, so 39 is yttrium, which symbol is Y. And so its atomic number is 39. The number of protons is also 39. And then for neutrons, we have to subtract. So atomic mass minus electrons, 89 minus 39. And so we end up with 50. And that's how you do that. The last thing that we're going to talk about is we're going to talk about isotopes. Now, they were mentioned earlier in this presentation in Dalton's theory, where atoms are a little bit different than other atoms even though they're the same type. And so what it is, it's an atom of the same element with the same atomic number but a different atomic mass. The same atomic number but different atomic mass. So they still have the same number of protons, but if they have a different mass, that means they're going to have a different number of neutrons. So having more or less neutrons than normal. And so we're also going to introduce another term, which is the mass number. It's kind of like atomic mass, except it'll never be a decimal number. And what the mass number is the sum of the protons and neutrons in an atom. So all the protons and neutrons added together is the mass number. So now the symbols for them are actually a little bit different. The symbols for it will actually have to give you some numbers. And so we have an example here for lithium where you see a 6 and a 3. What that 6 is the mass number. So that's the protons and neutrons added together. Now the bottom number, and you might be able to figure this out if you look at the periodic table, the bottom number is the atomic number. So for lithium, the atomic number is always going to be 3, but the mass number could change. Now how we name them is a little bit different too when we're dealing with isotopes. We have to tell people the number that goes with it. And so we use its normal name, and then we put a dash, and then we put the mass number at the end. So it's telling people that it's lithium 6 versus lithium 7 or lithium 8. Alright, so now let's try the similar chart that we did earlier, except now dealing with isotopes. So I've given you an isotope name, carbon-14. So the symbol for it, well, it's still carbon. Okay, but now we need to put some numbers in. So carbon-14 means that the top number is 14. The bottom number, when we look at the periodic table, we can see that carbon has an atomic number of 6. If it's got an atomic number of 6, that means the protons are 6. Electrons are equal to protons, so electrons are 6. And so to figure out the number of neutrons, what we need to do is we just need to subtract these two numbers right here. 14 minus 6 is 8. Okay, so when we look at the next one, we have carbon-12. So it again is carbon. Top number, 12. Bottom number, well, it's still carbon, so 6. Number of protons, 6. Number of electrons, 6. Number of neutrons, we subtract these two numbers, and so we get 6. And so you can see what's happening here, and I think the next column or row would actually be really obvious. So for carbon 13, well, it's going to look the same as the other ones, except it's going to be 13 over 6. The number of protons, well, that's 6. Number of neutrons, we have to subtract. So that's going to give us 7. And then the number of electrons is 6. So let's try krypton, because that's at least a different element. So the symbol for krypton is Kr. The top number is 83. The bottom number for krypton is 36. So that means that I have 36 protons, 36 electrons, and then I have to do a little subtracting right there. And so when I subtract, I get 47 on that. Okay, and then the last one is tungsten. That's kind of a fun element. You might have a hard time finding that one. It's kind of down in the middle and the bottom. But the symbol for tungsten is W. And so its top number is 185. And then the bottom number is 74, which means the protons is 74, the electrons is 74. And then I have to do a little bit of subtracting. And so that gives me 111 neutrons. All right, and there's the screen with all the letters so you can actually read them. All right, the very last thing that we're going to be doing is we're going to be calculating atomic mass. What an atomic mass is actually a weighted average of all the isotopes of a particular element. That's why the numbers on the periodic table are hardly ever a whole number. Now there are a few cases where there are whole numbers. You'll see them in parentheses, and what that means when you see them in parentheses is that there's only one isotope known for that particular element, so they can't do a weighted average. But for everything else, they look at the abundance of each of the types of atoms that there are, and then they average them together to get that. So as an example, when we look at carbon, and my periodic table might be a little different than yours, but carbon on here has a mass of 12.011. What that tells me is that the most abundant type of carbon in the entire world is carbon-12, because the mass is pretty much 12. But there must be something that's a little bit bigger, maybe some carbon-13 or some carbon-14, that makes that average be just a little bit bigger than 12. But it does tell me that the most abundant is 12. Let's look at another element. Find chlorine. Now chlorine on my periodic table has a mass of 35.45. And so what that tells me is that probably the most abundant type of chlorine is chlorine 35. However, there must be an awful lot of carbon-36 around too, which is why that average is kind of in the middle. And then the last one we can look at is boron. On my periodic table, boron has a mass of about 10.8. So what that tells me is that the most abundant type of boron that there is boron 11. Even though there's probably some boron 10 around, and there may be some other numbers even around. Alrighty, so the last thing that we're going to do is we are going to calculate an atomic mass. And it's actually really quite simple to do. How the problem will give you is that it'll give you the different types of elements that you have and the percentage that each one of them occurs. And so the first thing that we need to do is we need to convert each of the percents to decimals. And so just a refresher on that, all you've got to simply do is take that decimal, and I don't know if I can write this tiny, but take that decimal and scooch it over 2 places. Okay? And then we'll do the same with this one. Take that decimal, scooch it over 2 places. Okay? So what we've got is we have got copper 63 and copper 65. And then that is, they're now decimal. We changed the percent to a decimal. So we have 0.691 and 0.309. So what we need to do with each of those decimals is we need to multiply it against the mass. So here's the easy question. What's the mass of copper 63? Well, it's 63. And copper 65? It's 65. So then what we need to do is we need to multiply. So we're going to multiply 0.691 times 63. And separately, we're going to multiply 0.309 times 65. When we do that, we get these numbers, 43.533 and 20.085. Now, the last thing you have to do is just simply add those things together. When we add them together and watch for significant figures, which we're allowed 3, we end up with a mass of 63.6. Now, one of the things that people want to do is they want to then, it's like, well, I had 2 things, I'm going to divide by 2. Make yourself a note right here. Don't divide. Okay, you simply just add those things together and walk away from it, and then that's how you calculate atomic mass.